All right, so we're going to take a look at this equation. Copper oxide plus hydrogen yield copper plus water. And the question is, what is the energy change for this reaction? So you can look up in a handbook or in your own textbook the heat of formation for any single molecule. It will have elements on the left and the molecule that you're forming on the right. Now, we're going to start here with this. Copper oxide yields copper plus oxygen. When you look it up in your textbook or in a chemical handbook, it's going to look like this. The molecules are always on the right, the elements are always on the left, because it's heat of formation. So to form 1 mole of copper oxide, 37.1 kilocalories are given off. This is an exothermic reaction. Then you go up here. It's not a product here, it's a reactant, So what I've done is I've taken this and I've reversed the direction. So I put my copper oxide on this side. But when I did that, I reversed the sign and made it positive 37.1. Thank you. Perfect. Now we go to this. If we look this up in a handbook, it's the heat of formation for a mole of water as a gas, and that's minus 57.8 kilocalories. Well, we don't need to reverse direction on this because in the equation that we want, it is a product. And then we never use heats of formation for elements. They already exist. So we're going to drop them out. So we've got our copper as a reactant, our copper oxide, and our water as a product. So we're good to go. So now, Hess's law of summation, all we have to do is add up 37.1 kcal for the first delta H and negative 57.8 kcal for the second delta H, and we have overall, we find that this reaction overall is an exothermic reaction, giving off negative 20.7 kilocalories for every mole that we get here. Okay, we're going to take a look at another problem. This problem is 2 carbon monoxides plus 1 oxygen gives us 2 CO2s. We're going to use our little algebraic formula here that the delta H is equal to the sum of the heat per mole of product minus the sum of the heat per mole of reactant. So you can have a whole bunch of products and a whole bunch of reactants. You could still do this. You just sum them. Our oxygen drops out because oxygen is a what? No, it's an element. These only deal with molecules, not with elements. You notice we have brackets here. If you forget which comes first, it's alphabetical order, PR, product minus reactant. Okay, now we plug this in directly from our equation. What's our product? CO2. How many moles? 2. Do you get that? Sure. And what is our reactant? Carbon monoxide. How many moles? 2. And now we look it up on our table of heats of formation. We just look it up. And we find that to form 1 mole of CO2, it takes minus 94.1 kilocalories. And to form 1 mole of carbon monoxide, it takes a minus 26.4 kilocalories per mole. And actually it's given off, and in this case it's given off. Now, we said before, if you use Hess's law, when something is a reactant and the table gives it to you as a product, you have to reverse the flow of the equation and reverse the sign. When you use this equation, this minus sign does it for you. I would suggest that you use this because that reversal of the sign is already done for you. You just have to plug your reactant in. Notice also, when we plug in numbers, I'm using parentheses instead of brackets. Brackets are when we use formulas, and parentheses are when we use numbers. And if you calculate this out, you find 2 times a minus 94.1 minus 2 times a minus 26.4 is a negative 135.4 kcal. So the overall change in heat energy for this whole reaction is that it's exothermic, right? Right?
Right.
How can you tell?
Because the blue is negative.
Because the sign's negative. Very good. Huh? All right. Some stoichiometry. Suppose you are given 11.5 grams of ethyl alcohol. The formula I've written here, 2 carbons to which you've got the 5 hydrogens attached, and on the end carbon you've got your alcohol group, OH, the hydroxyl group. If you have 11.5 grams of ethyl alcohol, C2H5OH, and there's 46 grams per mole, which you would find by adding up their weights from the periodic table, / out go your grams, and then you look up on a standard heat of formation table, and you find that when you form one of these, you have 227 kilocalories used. Then the stoichiometry tells you that when you have 11.5 grams, to form it, you would use 56.8 kilocalories. To burn it, you would release 56.8 kilocalories. For the next problem, we're going to use hydrogen bromide plus chlorine gas yields hydrochloric acid plus bromine gas. Are we going to deal with the chlorine or the bromine, yes or no? Why? Because they're elements. We only deal with molecules. We'll use our formula, delta H equal the sum of the heat per moles of product minus the heat per mole of reactant. We simply plug our values in. The product, the only product that we're concerned with, because this is an element, is HCl. The reactant is HBr. We go to our table of values and we find that to form a mole of HCl, you give off 22.1 kilocalorie per mole, and to form hydrogen bromide, you give off 8.7 kilocalorie per mole. When we plug them in here, we get a negative 26.8 kilocalorie. Therefore, this entire reaction is what? Exothermic or endothermic? Exothermic. How can you tell? Negative sign. Our last calculation for today will be to use 11 grams of propane, knowing that every mole of propane gives off 531 kilocalorie when you burn it. You simply do a gram-molar conversion. You use your values that you get from a chart in a textbook or a chemical handbook, and you can tell that to form 11 grams, you would have to use 133. To burn it, you would get 133. Burning it is exothermic, and you can tell that again because of the minus sign. And that's as far as we're going to go for today.